If there are no questions, then we'll get started. I want to talk about the titration lab. You have no instructions for the titration lab, basically, but it's very simple. You know what we do in the titration lab? We do a titration with a pH meter stuck in there. So typically, you do a titration with a Erlenmeyer flask. We can't use an Erlenmeyer flask because of the pH probe, and so we're going to do the titration in a beaker. And so this is what we're going to do for this. We're going to be collecting the pHs at different intervals. And so before you even start the titration, you got to measure its pH. And so each of these X's will represent a measurement, like that. And then we have some milliliters of sodium hydroxide that we're going to titrate in there. And so we have an apparatus, it's set up. We got the beaker here, and we're going to put this on a stirrer. The stirrer, you have a little magnetic stir bar that's Teflon coated, and so you just drop that into this and then put your solution in here. Now, the trick here is this. The trick is we want to start off at the lowest pH possible. You know, but the pH of an acid, this is some kind of unknown acid, and it's a weak acid. And so I'll just call it weak, unknown acid. So we got a weak unknown acid in there, but you know, do you want to add water to it? Let's say if you keep adding water, what will happen? Without even adding any base, what's going to happen? The pH is going to go up. Is that a titration? No, that's a solution dilution. And so, you know, if we do more and more water, the pH is going to go higher and higher. Eventually, it's going to be so dilute, the pH is going to be 7. And that leads to a problem, because if we start off at a pH of 7, are we going to see much of a titration curve? No. And so this is the goal of the first part of the experiment. The first part of the experiment is to dissolve your acid in a maximum of water or minimum of water? Minimum of water. And so this is why I don't like instructions for this lab, because in instructions they're going to pick a volume of water that will dissolve all the unknown acids, which is too much for some of the acids. And so what we try to do is we try to just dissolve the acid and saturate the solution as much as possible. But for some of your acids, they're highly soluble. And so it doesn't take much water. You know, if you have a highly soluble unknown acid and you just add it, you know, a little bit of water, it all dissolves, then we run into another problem. That is, it's great because your pH is going to be low, but it's bad because the pH probe needs to be submerged in here. You know, wherever the sensor is, and we have two different kinds of pH probes. We have ones that have a little glass bulb on the end. That glass bulb is filled with a solution. The glass bulb is very thin, and the glass turns out to be pH sensitive. What happens is it generates an electric voltage, that is more ions on the outside or more ions on the inside. You know, if you have more ions on the outside, positive ions, and fewer ions on the inside, you know, you get an electric difference. That electric difference results in a voltage. And so we generate voltage. The voltage is typically millivolts. And a pH meter is just a voltmeter. It's a voltmeter. It's a fancy voltmeter because rather than reading volts, millivolts, it reads, you can calibrate it so that it reads pHs instead of millivolts. So anyway, we need enough solution to cover the probe. And I think we're using glass. And so there's a bulb here, and that bulb has to be completely submerged. Otherwise, you aren't going to get an accurate reading. Now, what happens if your unknown doesn't dissolve? Gosh, you know, you've been stirring it, you've been trying to crush up the crystals, and it just won't dissolve. And you're worried about adding too much, like 200 mil. If you're adding 200 milliliters of water to dissolve it, this is way too much, right? And so what do you do in that case? Yeah, heat it up. If your unknown is unwilling to dissolve, heat it up on a hot plate. You know, get it to close to boiling. Get it to dissolve, and then take it off and cool it down. You know, cooling it down takes time. You don't want to do the pH at high temperature, do you? No, because the temperature will impact the pH. And so one way of cooling it down is to run it cold water on the outside of the container. You know, or get some ice from the stockroom, put it in an ice bath. You know, cool it back down to room temperature or close. You know, it doesn't have to be exactly room temperature, just close to room temperature, and then we're good to go. The other alternative is to just leave it undissolved, but make sure it's totally dissolved by the time you hit the equivalence point. You want to make sure we don't call it the end point because we're not stopping there. We're just going to keep going. Keep going. All right, so can you summarize what I just said? I didn't write it down, but okay. One, we got to dissolve it in minimum or maximum? Minimum water, right?
It doesn't dissolve.
Yeah. If it doesn't dissolve, and you don't want to add too much water, heat it up. Good.
If not, just wait until it's dissolved by the time it's dissolved.
Right. Right. Good. Is there a reason why we want to start at a low pH rather than a high pH?
We just want the curve to show.
Right, because let's say the curve is supposed to look like this. You know, the higher the pH you start at, the less of that curve you're going to see. You know, so the more dilute this is, the less pronounced that equivalent point is going to be. It's going to look like this. And if you make it super dilute, you know, it might look like this. You barely see anything, just a little ripple rather than a wave, right? You want to see this. And so we don't want it overly dilute, because the pH can only go up when we add the base. So that leads to errors. This happens at the beginning, and it also happens at the end. You saw, you know, something where dilution is going to play an impact, and also solution concentrations are going to play an impact in seeing that third wave in what titration? Phosphoric acid. In phosphoric acid, we should see 2, 3 equivalence points, but we only see 1, 2 because the pH cannot get high enough to see that third. So here we might not even see any wave if the pH is too high to start. Well, anyway, what we want to see is what we call the structure of the titration curve. And what we want is a high resolution image of the curve, right? And so how do we get a high resolution image? Well, we take a lot of data. If we sample at very high frequency or very, small intervals, then we're going to get high resolution. All right, but the problem with high resolution is what? Yeah, it's a lot of data. Right? Each data point takes time to record. And so we would like to do it. Add a drop, measure the pH. Add a drop, measure the pH. Add a drop, measure the pH, but your titration is going to take 40, 45 mils. It's a lot of drops. We aren't going to have enough time. And so this is our compromise that we're going to make. We're going to take high resolutions when things are changing rapidly, but low resolution when things are kind of flat, not really changing. But the problem is this. The problem is this is an unknown acid. And so when do I know when to slow down and sample more frequently, or speed up and sample at larger intervals? This is why I want to schedule a full lab period, because every semester somebody screws it up you know, and has to redo it. And so hopefully they can redo it in the same lab period. But they screw it up because they take large intervals when things are changing big, and then tiny intervals when nothing's happening. And so they got it. But how can you know? How do you know when to slow down? Because this is, after all, an unknown acid. We don't know anything about it. Right? We don't even know how much acid to use. Yeah?
Do a quick test beforehand.
I'm sorry?
Run it fast beforehand.
Yeah. Yeah. We run a fast one beforehand, so we know. But we aren't going to run a pH titration because pH titration takes too much time. And so what we do is we run something called a trial titration. And so before we even start the pH titration, we have to do a trial titration to get an idea of where the equivalence point is going to be. So in a trial titration, we note this. If we have a diprotic acid, your acid is either going to be diprotic or monoprotic. You know, in Chem 1A, they told you, this is a diprotic acid, or they told you this is a monoprotic acid. In Chem 1B, we're not going to tell you because you should be able to figure it out based on the titration curve. Diprotic acid, you're going to see 2 equivalence points. Monoprotic, you should see 1. Now, for diprotic acid, the first equivalence point comes like this. Do you think the this is a typical, the equivalence points are going to be evenly spaced out. So if this is 10, then this would be another 10 milliliters. One thing you got to note about a diprotic acid is a diprotic acid, the first wave of this is small, usually. It's not totally symmetric where both waves are the same size, right? And so the first wave is usually small, which means this. Which means that I used to have a lot of trouble with this lab when I used the written procedure because people would add too much water. They add too much water, and the more water you add, the higher your starting point. And so people were getting this all the time, where they get just a tiny little blip like this. The tiny little blip here. And they ignore it and say this is monoprotic acid, when in fact it was a diprotic acid. And so this is one of the things that I thought, the written procedure isn't working. But now that people are trying to concentrate that acid as much as possible, then it's a little bit more pronounced. A little bit. But, even if you see a tiny little blip here, this should be what we call the, what's this region called? This should be the kind of the buffer region of a monoprotic. So if this were a monoprotic acid, it should be pretty flat, just a gentle slope there. And so if it's pretty flat and there's a little blip there, what do you think? The reason I'm asking you is because I get this question all the time. I see a little blip there. What should I do? Well, what would you do? I don't tell them. I don't tell them because, then it's like a crutch. They're always asking somebody, And you can't always have somebody to ask. You have to figure it out on your own, right? And so this is why we have the formal lab write-up for this lab too. This is going to be a formal lab write-up so you can talk about these kind of things. I thought I saw a little blip there, but I'm going to ignore it. Or, that little blip is probably indicative of a diprotic acid. And so the formal lab write-up for this is good because sometimes figuring out what your unknown isn't so clear cut. Well, anyway, going on with this, if it's diprotic, then the first equivalence point here has a pH less than 7. The second equivalence point here has a pH greater than 7. So if we have a monoprotic acid, diprotic, if we have a monoprotic acid, pH, mils, a monoprotic acid looks something like this, just one curve here. And the equivalence point is going to be at a pH greater than 7. So if we use phenolphthalein, where does it start to turn light pink? Well, at a pH, pH is equal to pK plus or minus 1. And so the pK is 9, so it starts turning around 9, but really the change happens around 8 to 10 is the transition region. 8 to 10, and then after 10 it's going to be solid red. And so if we use phenolphthalein, where would we see phenolphthalein start to turn red? At pHs around 8, right here. And so we hit it here. At pHs above 8, we hit it here. And so phenolphthalein would never see this because it'd be colorless. And where the transition is here and here. And so what we're going to do is we're going to do a phenolphthalein titration. So let me do that over here. It's just your standard titration. You know, you get a little sample of unknown. Now, how much unknown should you use in your titration? You have to guess, right? You don't want to use too much, because if you use too much, what's going to happen? You're going to have to, well, yeah, we'll use a little bit more water for dissolving, but if you use too much, chances are you're going to have to refill the burette, maybe multiple times. I had one person on the third refill of the burette. The third refill of the burette, they're doing, what are they doing with the container? 600 milliliter beaker they're titrating it in. That's way too much, right? And so what's the optimum amount of titrant you want to use in a titration? Under 50. Above 0 and under 50, because our burette holds 50 milliliters max. So we want to keep it below 50, right? But you don't want to go too small either. Because if you go too small, I had people do trial titrations which took 1.2 milliliters. If it only takes like, actually I should be more precise, like 1.21 milliliters. If your titration only takes 1.21 milliliters, then what's the problem there? Well, 1.21 milliliters is about how many drops? 25 drops? No, less. 22 drops. 22 and a half drops, something like that. It's like 23 drops. If you have a 1 drop error, or 2 drop error, or 3 drop error, and you only have 23 drops, what kind of percent error is that? Very big. Versus if you have a 1 or 2 or 3 drop error and you have, 100 drops or 200 drops, then it's a more manageable error. It's only like 2% or 3%. And so we don't want the volume too small, because if the volume of titrant is too small, the problem is the percent error becomes very large. And so what we want to do is we want to hit the end point. In a typical titration, we want to hit the end point between, let's say, 30 and 50 milliliters, right? That's what we want to do. But in this titration, what we want to do is we want to target this here at about 30, say 35 mils, roughly. Let's keep it simpler, like 30 mils here. Well, why do we want to stop at 30? We aren't stopping, because in a pH titration we have to go beyond this, right? And so this gives us some room to go to 40 mils, all the way up to 50 mils if necessary, to see the last part of the curve. And so the trial titration serves two purposes. The first purpose is to determine the optimum sample size. Because if your trial titration, you're hitting the equivalence point here when phenolphthalein turns red, you know, at way less than 30 mils, then you got to increase the sample size. Or if you're hitting the equivalence point close to 50 mils, then you got to decrease the sample size. Does that make sense? And so with a trial titration, we can determine, you know, what the optimum sample size is. So for example, if you hit the end point in the trial titration at 10 mils, then triple the amount of acid, so you hit it at 30. All right, the next purpose of the trial titration is to do this. Now we know we should be hitting the end point around 30. That tells us that we need to slow down before 30 milliliters and start collecting data at higher frequency, that is smaller intervals. Remember, this is just like 2 to 4 drops and it's already done. And so you want to tighten up the intervals here. Tighten up the intervals here. So before 30, now how accurate is yours? Well, you gotta account for error. You know, if you have a 1 drop error in your trial titration, 2 drop error in the trial titration, you got to compensate for that. And so the way we're going to do that is we're going to, you know, slow down. Maybe slow down at 29. Or if you don't have that much confidence, it depends on how much confidence you have in your trial titration. You know, if you nailed it and you think you really nailed it, then, you know, maybe 29 and a half. But be careful, because people think they nailed it and missed it entirely. All right, so we collect data at smaller intervals, like drop by drop here. Right? But in this region, which we call the buffer region, is much changing. Not much is happening here. And so in the buffer region, we'll collect data at larger intervals, maybe like 1 milliliter or half a milliliter intervals here. We'll collect data. But the problem is, what if it's a diprotic acid? If it's a diprotic acid, then you better slow down at before 30, and you better slow down before 15, because you might miss it entirely. So if we were taking big intervals here, then we might have missed the second or the first equivalence point. And so here at before 15, slow down. At before 30, slow down. And then between these, we can collect larger intervals. But we also want to get something, because, you know, at the half equivalence point, what do we have? At the half equivalence point, the pH is equal to the well, let's go to the monoprotic. At the half equivalence point of a monoprotic, the pH is equal to the pKa. And so the half equivalence point is important. And so this is good. We're collecting data frequently here at the half equivalence point, which corresponds to the first equivalence point of a diprotic. But if we have a diprotic, then that means we need to collect at finer intervals here, right? Which would be the quarter equivalence point of a monoprotic, which nothing's happening here, but just in case we have a diprotic, we want a lot of data there so we can pinpoint pKa 1. And here we want to pinpoint pKa 2, because the pH should equal to pKa, right? And the pKa's are going to help identify the acid. Now, this is a formal report, so one of the things that happens is, not all the data agree, unfortunately. And so sometimes you have to make some kind of judgment calls, like, for example, which one do you think is more reliable? Or are they equally reliable for identification purposes? pKa1 or pKa2? 2. Why? Yeah, good. Exactly. What we were talking about earlier, dilution, missing it. And so this one's going to be much more influenced than this one from dilution effects. We'll change the pH. So we do that, and then we, from the equivalence point, we can calculate the molar mass, of the acid, because we have the grams. And then at the second equivalence point, it's 1 mole of acid per 2 moles of base. At the first equivalence point, it's 1 mole of acid per 1 mole of base. Here, for monoprotic, it's 1 mole of acid per 1 mole of base, monoprotic. And so we can identify these based on that. But basically, we're doing data collection here. And so what we'll do is we'll do a rapid trial titration just in an Erlenmeyer flask with a drop or two of phenolphthalein and titrate it visually, stopping at the end point. Okay, if that goes good, then we scale the sample size so that it should hit 30. And then we run our pH titration. And so let's put in some numbers here, and then you tell me when to slow down, when to speed up. Okay, so I'll collect the first data point here. And then the next data point can be a small interval or large intervals. Okay. Large interval, like a milliliter, probably. And tell me if I should slow down. Slow down because, yeah, this could be the pKa1 region of a diprotic acid. Okay, once we see something here, maybe nothing, it should be pretty flat. Okay, then what? Slow down. Here. So monoprotic is going to look like this. However, a diprotic will look like what? Yeah, we should start seeing the first equivalence point here. Okay, once I'm past this region, and something's happened or nothing's happened, then I can increase, and then I need to slow down at, yeah. Well, monoprotic, nothing's happening still. For diprotic, we'll get the pKa2. For monoprotic, pKa1 is at 15. And then we need to slow down when we approach 30. We want to catch this as much as possible, but it's hard because the pH just skyrockets rapidly. Okay, once the pH starts to flatten out again, then we can go large intervals. And really, if nothing much is happening, you can increase it, let's say 2 milliliter intervals. Get the last part of the curve. And so we'll take it out to 50 maybe. All right, so that's data collection for the pH titration. That's what we're going to do, and then we're going to analyze it later. Are there any questions with this? No? All right. Uh-huh. 22.5. Thanks. 22.5. Those are important volumes.
But we would have to adjust
You have to adjust.
in order to get.
Yeah, once you, let's say you have a dye product, once you see where it comes, then you can easily predict where the next one comes, right? If you have a mono product, then you can't really adjust. So you're there. Uh-huh. This is too flat here. It just gently increases. No, it doesn't go rapidly. For monoprotic, it just gently rises. So this is the pKa. And so the buffer region, the official buffer region is pKa plus or minus 1. So we go up, 1 pH unit here. Once we go up 1 pH unit, you better start to slow down. So let's say the pH at this point were, 4.8. And then all of a sudden you're at 5.8. Then you know we're starting to get close, because at 5.8, what equivalence point are you at? You're at the, not 11 tenths. Not 11 tenths, the 10 elevenths, right? I don't know if anybody said 11 tenths. I'm just trying to illustrate. You know you're at the 10 elevenths, which means how much more do you have left? Only 1/11 of the titration left. And so once the pH is climbed up, after 1 from 15, then, roughly you're at the 10 elevenths, which means you don't have much left at all. In this titration, you better slow down. If you aren't slowing down at that point, then you might miss it, which lots of people do every semester. Huh? I'm sorry. We don't care about the molarity. We just need to know how many grams. Yeah, this titration, we don't care about the molarity of the acid. We know how many grams, and from the stoichiometry here, we can figure out the moles, and we'll just get the molar mass. So the amount of water is not important, just you don't have to accurately measure how many mils of water you dissolved your acid in. Also, you could potentially, well, this is a pH titration, so it's probably not best to spray. In a trial titration, you do those, you could spray water in because the volume's fixed already. The volume of acid was fixed, like 25 milliliter pipette. If you add another 5 milliliters, well, that's okay, we're going to dilute it, but the moles of acid didn't change, so you'll just take the moles of base and convert it to moles of acid and figure out the molarity. All right, any other questions on this? What time do I have? Now, this is going to be a formal report here, but we still have the other one, the synthesis lab, so I want a second rough draft for that. But when I collect the next rough draft, I'd like you to complete as many sections as possible. I'll take a look at those. And so when do you want to turn in that one? All right, after spring break. Collect it. This one, I don't know if I'm going to collect any rough draft. Maybe I'll just take this as the final draft.
So when is it due?
The rough draft? Let's have it due, what, Tuesday after spring break? Is that okay? Let me talk a little bit about the fractional precipitation problem we were doing yesterday, and a little bit about pH, and then I'm going to have a little quiz. What do we, what was the separation? It was iron 3, right? It was iron 3 with, and so we have some iron 3s in here, and magnesium ions, is that right? We have some magnesium ions in here. And then we have other ions in there too, because we got to maintain electrical neutrality. Right now, the hydroxide is very low, right? We haven't added any hydroxide. So let's just say that when we look at QSP here, we look at QSP for magnesium hydroxide. The QSP for magnesium hydroxide is the magnesium ion concentration initial times the hydroxide ion concentration initial squared. What was KSP for? Well, anyway, the magnesium concentration was 0.100. The hydroxide ion concentration is 10 to the minus 7. 1 times 10 to the minus 7, 1.0. 1.0 times 10 to the minus 7, just water, squared. Which comes out to what? And so there's some hydroxide. Is there very much hydroxide? No. The hydroxide just comes from water collisions. So a tiny bit of hydroxide in there. So what does this come out to? Well, this is 10 to the minus 1, 10 to the minus 14. Would it be 10 to the minus 15?
Yeah.
Did I write the KSP of magnesium hydroxide? Can somebody just look that up in the book really quick? Or did I write it down?
Uh,
1.9 times 10 to the negative 13. So KSP is equal to 1.9 times 10 to the negative 13, which means that KSP is bigger than QSP.
Right, the raw magnesium hydroxide is 1.8 times 10 to
1.8 times 10 to the negative 12? 11? All right. 1.8 times 10 to the negative 11. KSP is bigger than QSP. Therefore, what happened? No. QSP is less than KSP. That's unsaturated. QSP is less than KSP. I said KSP is greater than QSP, but QSP is less than KSP, which means it's not saturated, which means nothing's going to happen. Let's look at QSP for iron 3 hydroxide. And so this is just going to equal the iron 3 concentration times the hydroxide ion concentration cubed. And so the iron 3 is 0.100. Hydroxide is just from water, 1.0 times 10 to the minus 7 cubed. We're assuming. So this is going to be 10 to the minus 21. No, is that right? Yeah, 21, 10 to the minus 1, 10 to the minus 22. All right, and then what is the KSP for iron 3 hydroxide? Okay, 4 times 10 to the minus 38. All right, when you see extreme differences in KSP, this is 10 to the minus 11, this is 10 to the minus 38. Which one is more soluble? Which one's less soluble? More soluble, less soluble. But sometimes when they get close, it becomes very tricky. The reason it becomes very tricky is sometimes the species with the smaller KSP is actually more soluble. How can that happen? Is that true or false? Can a species with a smaller KSP be more soluble than a species with a bigger KSP? True. How that happens is because of how solubility varies. Here, solubility is the cube root of the KSP. Over here, the solubility is going to be the fourth root of the KSP. And so depending on how it ionizes, the dependence is different. It's totally nonlinear. Does that make sense? In other words, sometimes the solubility is the square root, sometimes it's 1/4 the cube root. Do you guys remember some of those yesterday? And so we have to be careful comparing KSPs. We can't just compare them directly because we have to see, is the solubility the square root, the cube root, the fourth root? What is it of the KSP? And that depends on how it ionizes. So be careful of that. But, you know, these are so different, you know, many orders of magnitude. It's pretty clear that this one's going to be less soluble even though they ionize differently. But if you're ever unsure, you just do the calculation. See what the solubility is equal to. All right, and so what this means is that the QSP is less than the KSP. Is that right? No. Actually, this is wrong. The QSP is actually greater than the KSP. Which means that if the hydroxide concentration got up to 10 to the minus 7, if this were pH 7, at pH 7, iron 3 should have already precipitated, whereas magnesium, there's not enough hydroxide to saturate it. And so nothing happens with the magnesium. And so this means that precipitate. And so in this particular separation, we have to start under acidic conditions, right? We start under acidic conditions, otherwise iron 3 is going to already be precipitated, which is okay. I mean, we could start here because the magnesium, has the magnesium precipitated yet? No, it hasn't. But anyway, yesterday I started under very acidic conditions and then start adding hydroxide slowly, and then we saw that the iron 3 becomes saturated at a pH of 1.86. 1.86 is super acidic, isn't it? But the situation is iron 3 is so insoluble you barely need any hydroxide to precipitate it out. And the hydroxide, that tiny bit of hydroxide present in the very acidic solution that comes from just a small fraction of water molecules colliding to make hydroxide, is enough to precipitate out the iron. And then as we continue to add more hydroxide, what's going to happen? As we continue to add more hydroxide, more and more iron precipitates out, because as the hydroxide increases, the iron must decrease to maintain KSP. KSP is a constant, so this product, iron product, is equal to a constant. And so we just continue to increase the hydroxide, but the problem is, if we continue to increase the hydroxide, eventually magnesium is going to get saturated and it will begin to precipitate out. And so tell me, at what pH will the magnesium start to precipitate? Go ahead and calculate that for me. At what pH will the magnesium start to precipitate? Did I set up the calculation already? I think I did. We just didn't finish it. I just wanted to finish it, I think. Or did we already finish it? We didn't. So will you finish it for me right now? And tell me at what pH does magnesium become saturated? All right, does somebody have it? 9.127. So,
Did we do that last time?
I think so. The hydroxide has to be greater than or equal to the KSP divided by the magnesium concentration square root. Is that what you got? And so what was the hydroxide ion concentration?
1.34.
1.34 times 10 to the minus 5. And so we have to start increasing the hydroxide until it hits this. Once the concentration hits this, then QSP is equal to KSP and it's saturated. So that if I exceed this concentration, it'll start to precipitate. And so the pH here is 9.127. Okay, thanks. And so once I hit this pH, it's saturated. This is the pH I need to stop at. Because if I exceed this pH, then both magnesium and iron precipitate. So beyond this, both magnesium and iron precipitate. So at this hydroxide concentration, at the stopping point, how much iron 3 plus remains unprecipitated?
Very small.
It's very small, and so we need to calculate it. And so the amount of iron 3 plus that remains, we calculate like this, is equal to KSP divided by the hydroxide concentration at the stopping point, Q. And so the hydroxide concentration at the stopping point is going to be 1.34 times 10 to the minus 5. We don't want to exceed that. And so let's go ahead and calculate the iron 3 remaining. Does somebody have it? Okay, I want you to do that. Calculate the iron 3 remaining, and then tell me the percent iron 3 that remains, and the percent iron 3 that precipitated at the stopping point. Okay, does somebody have it? Okay, the percent iron remaining, you got 1.66 times 10 to the minus 20% remaining, and then the percent precipitated is
1 minus about 99.99.
all right, 99 point. How many nines?
19.
19 nines. Okay.
That's just my estimate.
That's just. What would your calculator give you?
100.
100%. All right. So let's round off there. It's okay. All right, we're good with that. Actually, I'm not going to cover the pH part now because of the time, but I want to talk about today's lab. Today, one of the ways I'm going to shorten today's lab is we're just going to measure the pH of different solutions. And so we want to get familiar with our pH setup. It's going to be the same pH setup we used in Chem 1A, the LabQuest. You guys remember that? LabQuest. Some of you might not have used it, LabQuest. But today we'll get familiar so that Tuesday we can jump right into the titration. We're going to measure the pH of some of these solutions, but we could also calculate the pH of a lot of these solutions. So somebody give me a list of the solutions that we're looking at. Yeah. What are the solutions and the concentrations that we're looking at today? What is it? Sodium chloride. What molarity? 0.100 molar Well, it's really going to just be 0.1 probably. It's not made so precisely. 0.1 molar sodium chloride, you know, what should the pH be? pH should equal 7.0. So these are our calcs. What's the next solution? Sodium acetate, 0.1 molar sodium acetate. Actually, we did this calculation recently, wasn't it? Maybe not. The pH should be greater than 7, less than 7, or equal to 7? Greater than 7. How would I calculate it? For the calculation, you need to do a Kb and would you do a Kw? Or would you ignore the Kw? 0.1 molar, we'd probably ignore this. Not necessary. Okay, what's the next? Ammonium chloride. 0.1 molar ammonium chloride. Ammonium is an acid, chloride is neutral. Base, neutral. And so the pH should be greater than 7. And to do the calculation, you would do a Ka of ammonium and oops, yeah, ammonium's acid. So pH is less than 7, and for the calc, we do Ka and Kw, or would you ignore the Kw? Probably ignore the Kw for ammonium chloride. So we just probably do a Kb, Ka calculation here. All right, what's the next solution?
Zinc chloride.
Zinc chloride, 0.1 molar zinc chloride. Now, this is tricky. This is tricky because metal cations can be Bronsted acids as well. Except metal cations except for group 1 and group 2. We'll just say calcium, strontium, barium. There's some more. Metal cations except for group 1 can be Bronsted acids. You know, the iron 3, if we measured iron 3 nitrate, what do you think the pH of iron 3 nitrate is? It cannot be 7. If the pH is 7, you know what's going to happen? We get some precipitate in there. So the pH has to be low. But the thing about iron 3 is this. Iron 3 forms a hexa-aqua complex. And this hexa-aqua complex can undergo Ka reaction hydrolyzing water. And so one of the protons in water in the aqua ligand is lost, and that aqua is converted into a hydroxo, and we end up with 5 aquas now, like this. And the charge goes to 2 plus, the overall charge, plus a hydronium. And so what happens is when water is bonded to a metal, we have a strong inductive effect. You remember the inductive effect? Inductive effect is you have this iron 3 plus pulling electron density away from oxygen, which makes oxygen pull the electron density more severely from the hydrogens, resulting in a very large delta plus on the hydrogen. Yeah. So hexa-aqua iron 3 is considered triprotic acid because it has the possibility of losing a proton on one water, on another water, and then forming iron 3 hydroxide. And so this Ka is bigger than acetic acid. And so that means that iron 3 is even more acidic than acetic acid for a given concentration. It's fairly acidic stuff. And so zinc 2 plus, Zn2 plus is an acidic ion. Chloride is neutral. And so the pH should be less than 7. Now, if we wanted to calculate the pH, then we would need to know the Ka for Zn2 plus. All right, what's the next species? I'm looking up the Ka for Zn2 plus. And what is it given? I had it and then I lost it somewhere. I don't know where I put it.
It's K.
K
A-L.
A. Okay. K-A-L.
And then parentheses SO2.
SO 4 2. Potassium aluminum sulfate. This is mixed cation salt, right? Potassium ions.
I see it.
Potassium ions. Neutral. Aluminum ions. Well, aluminum, if you looked on the acid chart in our classroom, this one occurs on the acid chart in our classroom. We have the hexaalkyl complex of aluminum 3 plus H2O liquid yields what? Yes, Al, OH, H2O, 5. Net charge, 2 plus hydronium. Ka for this, actually the K for that might be in your book. But since we're not in the classroom, let me see if I can get it for you. Quick. .9 times 10 to the minus 6 from the internet. I'm not sure how reliable that is, but we'll just use it. Ka is 7.9 times 10 to the minus 6. I forgot to write it down earlier. Which means it's less acidic or more acidic than acetic acid? Less acidic. Sulfate. This is sulfate. Sulfate is not neutral. It's a base. This is what we call a dibasic base. And this is going to have a Kb1 and a Kb2. And I'll tell you what the Kas are. For H2SO4, you know, Ka1 is very large. And Ka2 is pretty big. Ka2 is 0.01. 0, which is kind of big. This is why we have to worry about Ka2. Normally we ignore Ka2, right? But a Ka2 this big is like 0.01 is significant. And this is why for water we would do, I mean not for water, for sulfuric acid we would do Ka2. Would we do Kw? 10 to the minus 14? No. Alright, and so today's quiz is going to be a little bit different. It's not going to be a reactions quiz, but the same rules apply. You can work with anybody and use whatever resources you want, except don't go asking other instructors. It happened with the last quiz, and it came back to me. And then, yeah, but everything else is okay. I want you to determine the pH of this solution. It's 0.1 molar. Okay. 0.1 molar. What is the pH? So calculate the pH of this salt solution. We'll have it. So after this quiz, then you can take a break, and then we'll start the lab.
Are we doing the buffer as well for the lab?
Are we going to be able to
Yeah. You have to calculate it. Are you going to be able to finish this lab? Yeah, I'm going to shorten it a little bit, so we'll be able to finish it. Yeah, we're going to do the buffer too. The buffer, you just mix up a buffer, and then but the buffer, this is what I want you to do for the buffer. You know, the buffer, they say add 10 milliliters. I don't want you to do that. I want you to mix up the buffer and then add it drop by drop while monitoring the pH and see. You know, you can see, okay, I'm still within buffer capacity, I'm still within buffer capacity, and then I want you to exceed the buffer capacity and watch the pH change more dramatically. And so I want you to see how the pH changes with added acid or added base, strong acid or strong base, and then once that capacity has been reached, what happens when you exceed it. Okay? And so, you know, you don't have to follow the experimental procedure strictly, and you know, the main purpose is, one, to familiarize yourself with the pH meters, and two, to see some of the pHs of these salt solutions. But this quiz I'd like you to do, let's take about 10 minutes for the quiz, and then a break, and then start the lab.
And for the report for this lab?
For the report for this lab, you just have your observations in your notebook, right? We aren't doing the lab exactly as written.